Hey everyone, and welcome to this deep dive made just for you. We're going to try to tackle a pretty big mystery today, and that's the Great Attractor. It's this huge invisible force that's pulling our galaxy, the Milky Way and a whole bunch of others, towards it.
Yeah, it's kind of like a cosmic whirlpool, but like on a scale that's, it's hard to even imagine.
So our mission today is to figure out where it is we're all going and what's behind this cosmic journey.
Right.
We'll be using a YouTube video from the channel History of the Universe called Where is Everything in the Universe Going?
Right.
And hopefully we can get to the bottom of this.
Yeah. It's really interesting to think about how our understanding of, how the universe moves has changed. I mean, for centuries, people thought that the Earth was the center of everything, that it was motionless,
Yeah.
But it took, a real shift in thinking, thanks to Copernicus, to realize that we're not actually stuck in the middle. We're actually part of this. It's kind of like a cosmic dance.
Yeah. It's like being in a car. We're so used to moving with the Earth that we don't even really feel the movement until we hit a bump, or slam on the brakes. But we're not just spinning around on Earth's axis. We're also flying through space as Earth orbits the sun.
And that's really just the beginning. To get a good sense of our place in all of this movement, we need to think about what's called peculiar velocity.
Peculiar velocity?
Yeah. It's not just about how we're moving locally, but also how we're moving compared to, the expanding universe. It's kind of like if you're on one of those moving walkways at the airport.
Yeah.
You can walk forward, you can walk backward, or stand still, but you're always being carried along by that walkway. And that's kind of similar to how our galaxy is moving, as part of the expanding universe. Okay,
I think I'm starting to see what you mean. So we've got Earth spinning, orbiting the sun, and then the entire Milky Way is moving within the expanding universe.
Yeah.
So, what kind of distances are we talking about here?
Well, get ready, because the numbers are huge. Just from Earth's rotation alone over a normal lifespan, you'd travel 1 billion kilometers.
1 billion kilometers?
Yeah, 1 billion kilometers. That's like going around the Earth 25,000 times.
Wow, that's like a serious frequent flyer program. But hold on, the sun's moving too, right?
Right.
It's not just staying put in the Milky Way.
You got it. Our sun's actually on a big trip around the center of the Milky Way. It's zipping along at about 230 kilometers per second.
Wow.
And it takes, roughly 230 million years to make one full orbit. And here's where it gets really interesting. That speed, it's actually one of the clues that led us to the idea of dark matter.
Dark matter. Okay, maybe we should break that down a bit.
Yeah, dark matter is this mysterious stuff. We can't see it directly, but we know it's there because of its gravity. You see, the speed of stars and galaxies, and that includes our sun, is much faster than it should be if you just look at the stuff the visible matter. So that tells us there's got to be something else there, something invisible that's adding extra gravity to keep everything from flying apart.
So it's like what, an invisible scaffolding holding the galaxy together, and this dark matter, it's like everywhere.
Pretty much. It's estimated to make up about 85% of all the matter in the universe. But here's another twist. Even with dark matter holding things together, our galaxy isn't exactly staying put. You see, we're on a collision course with our galactic neighbor, Andromeda.
Collision course? Now that sounds kind of intense. Should we be worried?
No, not really. It's more like a really slow-motion cosmic dance. It's going to take billions of years to unfold. So over the next 2 billion years, Andromeda will start bigger and brighter in our night sky. Then about 5 billion years from now,
Okay, you've got me hooked. What happens when these two huge galaxies finally meet?
Well, it's going to be pretty chaotic, but also beautiful. Just imagine, stars and gas are going to swirl together, collide, and trigger these bursts of star formation. So millions of new stars will be born from this cosmic battle.
It sounds like one heck of a light show. So what happens to our Milky Way in all of this?
Over a really long time, the spiral shapes of both galaxies, they'll dissolve and they'll merge into one giant elliptical.
Wow.
It's kind of like, two dancers becoming one, their individual movements kind of blending into a new unified form.
That's quite a picture. But how do we know this is all going to happen? I mean, do we have some kind of cosmic crystal ball or something?
Not magic, but it's close. We can actually use math and observations to map the movements of galaxies and try to predict their future.
Okay.
For example, we use something called the cosmic microwave background radiation. It's like an echo of the Big Bang. We can use that to piece together the history of the universe.
So we're looking back in time to see into the future.
You got it. And we also use math.
Okay.
There are these equations called the Mj-Onkenev equations that have been really useful.
Mj-Onkenev. Those sound pretty complicated.
Oh, they are. But what's really cool is that they were originally developed to solve logistical problems, like figuring out the best routes for delivery trucks.
Huh.
It's kind of amazing how tools designed for something so down to earth can help us understand, well, the grand movements of the universe. By combining those equations with data from the cosmic microwave background, we can build models and simulations, and we can see how galaxies have moved and where they're probably going to go.
So we're using math made for delivery trucks to map the universe. That's pretty incredible. And these tools tell us that we're zooming towards this great attractor. But is that really the whole story?
It turns out it's not that simple. Our motion towards the Great Attractor is really just a small part of a much bigger cosmic flow. You see, we're part of what's called the Laniakea supercluster.
The Laniakea supercluster.
Yeah. It's a huge collection of something like 100,000 galaxies, and they're all moving towards a common center.
Hold on, a supercluster? That sounds even bigger than a regular cluster of galaxies.
Oh, it is. Imagine our local group, with the Milky Way and Andromeda and a few dozen other smaller galaxies. Imagine that as a tiny village.
Okay.
A galaxy cluster would be like a small town, and a supercluster, well, that's like a massive city. Laniakea is home to hundreds of galaxy clusters, and they're all connected by, it's like a web of gravity and filaments.
Okay, I see. So is this Great Attractor, is that the center of Laniakea, this giant cosmic city we live in?
We think the Great Attractor is most likely what's called the Norma cluster.
The Norma cluster.
It's a really massive cluster of galaxies inside Laniakea.
Okay.
But here's the thing. Even with all of its gravity, it can't fully explain how strong our motion is towards it. That kind of suggests there's something even bigger out there, something that's influencing us, pulling the strings, on an even grander.
So what could be bigger than a supercluster that's pulling us toward?
We're talking about the Shapley supercluster. It's absolutely huge, contains hundreds of galaxy clusters, and it's located over 650 million light years away. Its gravity is so strong that it reaches out across hundreds of millions of light, and it affects the movements of galaxies and clusters all across this vast region of space. And that includes our own Laniakea supercluster.
Okay, so let me get this straight. We're being pulled towards the Great Attractor inside Laniakea, but Laniakea itself is being pulled towards this even more massive Shapley superclusters, like cosmic nesting dolls.
That's a good way to put it.
But if gravity is pulling everything together, shouldn't the universe eventually collapse in on itself?
That's where things get a little weird. Remember dark matter?
Yeah.
Well, there's another mysterious force at work, and it's actually working against gravity. We call it dark energy.
Dark energy? That sounds like something out of a sci-fi movie.
I know, right? But it's very real. It's this pervasive force that's actually making the expansion of the universe speed up. It's like the fabric of space itself is stretching and expanding, and it's doing it faster and faster all the time.
So instead of everything collapsing inward because of gravity, it's all being pushed apart by this dark energy.
Exactly. And as dark energy gets stronger, this expansion is going to get faster, and it's going to start tearing apart superclusters, clusters, even galaxies that aren't held together tightly enough by gravity.
So all those huge structures we talked about, the superclusters and clusters, they're not going to survive. What about our local group? Will it be ripped apart too?
Our local group is pretty tightly bound, so it will probably survive. It's like a group of friends holding hands in a strong current. If they hold on tight, they'll stay together. But those galaxies and clusters that are further apart, they'll eventually drift away from each other. It's kind of sad to think about it.
Yeah, it is. So what about our journey to the Great Attractor? Does that even matter anymore if everything is being pulled apart?
Well, the journey as we know it is basically over. Over billions of years, our movement towards the Great Attractor is going to slow down, then it's going to stop, and eventually it'll revert. You see, as dark energy takes over, all those gravitational pulls become less important.
So we're on this epic voyage towards this Great Attractor, and then dark energy comes along and changes the destination. It's like somebody moved the finish line.
It is a pretty big shift. And what it means is that the universe, as we know it, it's going to change a lot. Galaxies are going to become more and more isolated, like islands in a growing sea of darkness. Imagine looking up at the night sky billions of years from now. Instead of seeing that band of stars like the Milky Way, you might just see a few scattered points of light. The galaxies that manage to stick together,
That's getting a little existential. So it's like the universe is playing a cosmic game of musical chairs, and eventually the music stops, and everyone just left standing alone.
I guess you could say that. But even though these big structures are going to dissolve and galaxies will end up alone, the story of the universe isn't over. I mean, there's still so much we don't know about dark energy, and you never know There might be new discoveries out there, things we haven't even imagined yet, that could totally change our understanding of how it all ends.
Okay, that's kind of reassuring. I mean, the universe is full of surprises, right? But before we get too lost in all of that, maybe we should talk about another part of this story. Something that connects those big empty spaces we've been talking about, the voids, to the movement of galaxies.
Right.
I mean, these voids might not have any matter that we can see, but they're not really empty. They're full of dark energy.
That's exactly.
And that dark energy, well, it kind of has a repulsive effect, almost like an anti-gravity. It pushes things away from each other.
Yeah, you're right. Those voids are really important when we talk about how things move on a grand scale in the universe. It's not just about gravity pulling things together. It's also about those voids pushing things apart. And it's because of that push from the voids that we're never actually going to reach the Great Attractor.
Hold on. I thought empty space was, well, empty.
Yeah.
How can these voids actually push galaxies around?
Well, it's kind of like, imagine a loaf of raisin bread rising in the oven. The raisins, those are the galaxies. And the dough, that's the expanding space.
Right.
As the dough rises, those raisins get pushed further and further apart. Even though they're not actually moving on their own, the space between them, it's growing.
Okay, I can see that.
Right.
So the voids, they're like that expanding dough pushing the galaxies apart. But wouldn't that mean the galaxies on the edge of the voids, wouldn't they get kind of squished as the void grows?
That's a really good question, but instead of being squished, those galaxies are actually pushed into other structures. They become part of what's called the cosmic web.
The cosmic web.
It's this network of filaments and clusters that make up the large-scale structure of the universe.
Okay.
It's almost like the voids are kind of sculpting the universe, shaping where all those galaxies and clusters end up.
So it's not just random chance where the galaxies end up, these voids.
Yeah.
They're actually helping to make those patterns we see in the cosmic web.
Exactly. It's another way that everything in the universe is connected.
Wow.
But there's one more piece to this puzzle I want to share with you, something that connects the really, really early universe to all those big movements we see today.
Okay.
Remember those baryonic acoustic oscillations we talked about?
I remember the name, but maybe we can use a little refresher. What are they again? And how do sound waves from the early universe affect things billions of years later?
Okay, so picture the universe just a few 100,000 years after the Big Bang. It was so hot and dense, just a sea of particles and radiation. And within this crazy soup, sound waves were rippling through the plasma.
Wow.
Creating these areas that were a little bit more dense and others a little less dense.
So these sound waves were like ripples in a cosmic pond.
Exactly. That's a great way to think about it.
Cool.
And as the universe expanded and cooled down, those density differences, they got frozen in place.
Frozen sound waves, huh? So how do those frozen ripples affect how galaxies move today?
Well, over billions of years, those tiny density differences acted like seeds.
Seeds?
Yeah, seeds for bigger structures to grow, areas with a bit more density. They pulled in more matter because of gravity.
Right.
And eventually, they formed galaxies and clusters.
So those ancient sound waves basically made a blueprint for the entire structure of the universe.
Pretty much, it's like the echoes of the Big Bang are still shaping the cosmos today.
That's amazing. So those echoes, they're not just random noise, they form a pattern.
Exactly. It's like a series of overlapping shells where you find a slightly higher density of galaxies.
So wait, we can actually see these shells of galaxies.
Well, we can see evidence of them when we map out where all the galaxies are. And one of these structures, it was discovered recently, it's called Hulelana.
Hulelana. That's a beautiful name. What does it mean?
It's Hawaiian, and it means sent murmurs of awakening. It really captures what this discovery is all about. These ancient echoes of creation kind of whispering to us across these vast cosmic echoes. They help us understand how the universe transformed from this smooth soup of particles into the incredible cosmic web today.
This has been quite a journey. We started with Earth spinning and ended up talking about hurtling towards the Great Attractor, only to find out that dark energy is pushing us away. We talked about cosmic voids and ancient sound waves. It's mind-blowing, but it's also really inspiring.
It is.
So what's the biggest takeaway for our listeners today?
I think the biggest takeaway is that the universe is this incredibly interconnected and dynamic place.
Yep.
From the tiniest particles to the biggest superclusters, everything is moving and changing, influenced by forces that we're only just starting to grasp. And while we might eventually end up all alone as dark energy keeps pushing the universe apart, for now, we're part of this amazing cosmic dance.
Beautifully said. And on that note, I think we'll wrap up this deep dive into the universe. We explored the Great Attractor, the cosmic web, dark matter, dark energy, and those echoes of the Big Bang that are still shaping the universe today.
Right.
It's a lot to think about, but that's what makes it so fascinating. There's always something new to learn and explore.
Absolutely.
So keep looking up at the stars and never stop asking questions about the universe and our place in it. Thanks for joining us.